Hi students, today we're going to talk about solutions, specifically the properties of water and molarity and dilutions. Now I know this looks like a small amount of material, but it's actually not. There's a lot that goes into this. So first and foremost, we need to discuss the properties of water and how it ties into us making solutions. Most of the solutions you will encounter in everyday life are water-based. So the first interesting thing about water are its physical properties. The first one is its density. That we can see over here. Well, let me get my pin situated. There we go. So from zero or from negative infinity to 0 degrees Celsius, so whenever we have solid water, we can see in this picture that the water itself, the molecules, because it is so polar, it actually spaces out and becomes much less dense than the liquid water around it. So we can see the distance from this particle to this one is much less than the distance from this particle to this one, which is even smaller with these two particles. So the highest density of water is actually at 4 degrees Celsius. So 4 degrees Celsius, that's when the water is most dense. As you increase the temperature, the water becomes more mobile and they start moving around more, so they become less dense. So ice floats and actually insulates the water below it. So if you had a sheet of ice right here, everything below this would be insulated. This is very important for water life, as that is what keeps them alive when you have a layer of ice on top of them. That's why you can go ice fishing. Another important aspect of water physically is its high specific heat capacity. This is very important for things like animals because it helps us cool our bodies. So remember we talked about energy before and how if we were actually to just release the energy we have, we'd probably explode. Well, as we are utilizing this energy, our body heats up and our sweat glands produce sweat, which cools our body. So the energy gets transferred to the water evaporates, and that energy leaves our body that way. Now, dogs, or wolves, or canines, they don't have a lot of sweat glands. They have a couple sweat glands on their paws, but that's about it. So the rest of their body has to get cooled in some way. And that happens to be their tongue and how they pant. So they actually evaporatively cool their nose and their tongue with their saliva in order to regulate their body temperature. So water is very, very important. On the flip side of that, we have our chemical properties. Again, polar is very important because those hydrogen bonds are physically going to make them spread out when they get too cold and start forming solids. But hydrogen bonds also play an important role in how water interacts with its environment and itself. These are adhesive forces, so liking to adhere to things. So bonding or interacting a lot with the environment. And cohesions is interacting or hydrogen bonding with other water molecules, so themselves. These two things are very, very important for plants and animals alike. So the hydrogen bonds, when we are talking about So the hydrogen bonds, because we have those cohesive forces, water molecules tend to form hydrogen bonds and want to be next to each other an awful lot. This increases the surface tension and allows certain properties, such as water skitters and other animals, to actually skirt on top of the water. So what we're seeing here is this water strider, water skipper, whatever you want to call them. It has 1, 2, 3, 4, 5, 6 points of contact with the water. And those points of contact are spaced out and long. So this allows the water strider to make use of the bonds of the water at the top, those hydrogen bonds, in order to stay suspended above the water. Now, if we disrupt the surface tension of the water, these little guys will actually fall. And I'm going to show that in class this week. Cohesive forces play a major role in the surface tension, but the cohesive and adhesive forces together play a very large role in what's called capillary action. So in very, very small tubes, water wants to adhere to the sides of the tube, but they also want to stay together. So what happens is they form basically a plug inside of the tube. So in plants, we have water going all the way through the plant, and when that water evaporates out of the underside of these leaves, other water has to take its place. So through capillary action, that water moves through the capillaries, takes the place of the water that left, and pulls more water up. This allows the plants to continuously get water and to remain turgid or rigid. So that's what happens when your leaves wilt, is they aren't getting enough water. Since they don't have the water inside of them, they become flaccid and they just kind of droop over. This is also why we have rain that forms. Water wants to stick together, so whenever it gets close to each other, it sticks together in the clouds, forms water droplets, and then those fall to the ground. Now, the hydrogen bonds are formed mainly because water is indeed polar, which is actually very useful for water. Water tends to want to bond to just about everything that has even the slightest of charges. So it's been deemed the universal solvent. So everything but nonpolar molecules will dissolve in water because of how it interacts with itself and with others due to its polar nature. Now, water can dissolve those nonpolar molecules. However, it needs some sort of mediator to help it form what's called a hydration shell. And that's what is involved with water actually dissolving any and everything. So when we have a salt crystal, so when you put this on your eggs or you put this in some sort of liquid, the salt will actually dissolve into whatever water-based substance you have. And the way this works is whenever something dissolves, water, in this case, will align and surround the particulates, in this case the ions. They will surround them by the negative oxygens wanting to be near the positive sodiums and the positive charged hydrogens close to the negatively charged chlorines. Once they wrap them up as best they can with also keeping themselves spaced away from each other, as shown here, those oxygens don't want to be near each other, they form what's called a hydration shell. So when all of your particles are surrounded and all of your water is completely surrounding as many particles as possible and you have an even complete distribution and you can't put any more salt inside of your solution, it's called saturated. If it's saturated, you can't put any more dissolving inside of it because whatever is being dissolved by the water molecules, something else is releasing it back into the solid. So just like with equilibrium, there comes a time when your forward and reverse reactions are the same. Your forward dissolution is the same as your reconstitution of your solid. It happens. If you had more that could be surrounded, then you are unsaturated. So if you could add more sugar, add more salt to it, then it is unsaturated. If you increase the temperature, you increase the movement of the particles, and so you increase the amount of these hydration shells you can make at any one point in time, and it allows you to dissolve more particulates for the most part. Solid particulates, not gas, and we'll get into that in a second. So what you have then is called a supersaturated solution. You can have a supersaturated solution if you saturate a hot solid, or a solid into a hot liquid, and then you slowly cool it. Those hydration shells, while your solvent particles aren't moving around as fast, they're still keeping those ions that they did envelop away from each other enough that they're not forming any more crystals. However, if you ever so slightly disturb this cooled solution, you get really easy crystal formation, and I'm going to show that in class as well. So make sure you come to class. So there are some things that will increase your ability to dissolve things, or the rate of dissolution. So this is actually the rate of dissolving things. So surface area is first. As you break things apart, so let's say we had a pill right here. If I was to cut it in half, you would then have this half of the pill and this half of the pill. I know they don't exactly look like halves, but bear with me. So right here, you only have this top surface area to work with. Over here, you have this top of the surface area plus whatever part of the pill is exposed from when I cut it. Same thing for over here. So you've added a little bit of surface where the solvent can actually interact with this solid or liquid or whatever. So for surface areas, it's really, we're talking about the solids, unless you have a really, really dense liquid. So when you have this, as you increase the surface area, so let's say you have a sugar crystal right here, if you pulverize that and you make small sugar parts, you have way more surface area in the granulated sugar than you do in a cube of sugar. So once you have these guys, there's more room for the water to get in and surround it and form hydration shells. So that's the reason increasing the surface area increases the rate of dissolution or dissolving. Now, as for stirring, if we just drop that chunk of sugar into water, what happens is you actually get full hydration shells all the way around this. So if you've ever dissolved something, you might have seen this, where you get those ripples in the water. And so what you're seeing is you're seeing a little bit of a difference in density, and so it changes how the light passes through it. But what you're seeing is you're seeing saturation around this amount of solid. So if you stir it, what you're doing is you're breaking this dissolved particles away from this, allowing cleaner water to come in and continue to dissolve. So you get more even dissolution or dissolving. So it increases the rate at which the water can actually interact because you're getting rid of this saturated area around the solid. Now, temperature, it can help or hinder you dissolving things. So if you're talking about liquids or solids, so everything but a gas, as you increase temperature, the movement of the water particles increases, and so we are able to dissolve things quicker. So you're forming those hydration shells, you're moving things out of the way, and you're able to dissolve things quicker. And I'm going to show you this in class physically, so don't worry about this. Now, gases, on the other hand, they are a little bit different. So for gases, that movement is still happening. However, the movement of the water and the gases is happening. So at the top of your liquid, what you're going to find is as you increase the temperature, the gas, like CO2, will come in contact with the top of the liquid faster and leave more. So as this happens, you lose more and more of the gas as your temperature increases. So cooler temperatures actually do better for controlling how quickly the gas leaves the water. The same kind of principle happens with pressure. So say you have a liquid in a sealed container. As the gas particles leave, they bounce at the top and they come back into solution occasionally. Well, as you increase the pressure, there's less space, if we're talking volume-wise, if we're leaving temperature the same, there's less space, and so we have more of the gas entering the liquid. That's why your soda is pressurized. The higher the pressure, the less of the carbon dioxide leaves the carbonated beverage. So these are just some things that will increase the rate or change how much can actually be dissolved in what you're dissolving. So once you have things dissolved in other things, there are special ways that we actually talk about this, and those are called concentrations. So now we're talking about molarity and how we start doing dilutions. So concentrations, whenever we're talking about that, you're talking about how much of one thing is in something else. So for molarity, this one right here, that is the most common concentration that you are going to talk about. And its units are in moles of solute over liters of solution. So we're talking about the moles of something over the liters, or the volume of the solution. Molality is a little bit different, and so you have molarity and molality. So it's only difference by one letter, the R and the L. I know it's confusing. So that is the moles of solute over the mass, or in this case kilograms, of solvent. So we don't care in this one about the overall solution. So sometimes as you add your solute to a solution, the volume of the final solution could go up or down. So preparing a molar solution is harder than preparing a molal solution. Molal solutions, all you have to do is weigh out your solvent and then dump your solute into it. Now, we're not going to really use a lot of these, so that kind of doesn't matter. I mean, we're not going to use molality as much, so it's not really that important, but if you see it, this is the difference. And the other one that we're going to use an awful lot is the percent by mass. So this is your mass of solute over your mass of the entire solution. So that would be the mass of the solute plus the mass of the solvent. So mass of solution. And then all of this is times by 100% because your masses are going to cancel. So now for our first two up here, these require us converting from mass or getting to moles. So we have to have moles of solute. It's mandatory. You have to have moles. If you can't get to moles, you need to go back and revisit that from the first semester and get to be able to dealing with moles. Now for all of them, because we are dealing with units of measurement, either mass or liters, we have to be able to convert using the metric system. So if you need a refresher on that, go back and look at course 1 or quarter 1, and if you're still having trouble, you need to contact me and we need to have a meeting about that. So for the percent by mass, if you are given a liquid, so let's say water, the density of water is equal to 1 gram per 1 milliliter. That's the density. So if you are given a liquid, you will need to be able to get the mass from the density. And that's very, very important. So the way that you do that is you literally use our stoichiometric math. So if you have 30 grams of water, and I need to know, let me try this again. So our density is equal to 1 gram per 1 milliliter. So if we have 600 milliliters of water, I need to know how much mass that is. So for every 1 milliliter, there's 1 gram. So I should have 600 grams, because my milliliters would just cancel. So it's 600 grams of water. Now, different liquids will have different densities, so it's not always this easy to do a 1-to-1 ratio, but that's why water is so amazing. And we love water because water helps us out like this. So because the concentrations are already set up as fractions for all of them except a percentage, even percentage to an extent is set up as a fraction, we can use them in stoichiometric calculations, especially those with moles. So let's say you have a single replacement reaction. So you have zinc plus silver nitrate. And you're going to then have silver plus zinc nitrate. So zinc is a solid. We don't really care about it. However, silver nitrate dissolves, so it's aqueous. So let's say you had a question that said you have a 6 milliliter amount of 4 molar silver nitrate. How much zinc, mass-wise, do you need to react? Well, we can use all of our information to do this. So first, you're always going to want to start with anything that has moles in it or can get you 2 moles of something. So this 4 molar is actually 4 moles per 1 liter. So we're going to start there. So we have 4 moles in every 1 liter. We don't have a full liter, we only have 6 milliliters of this. So we need to convert from liters. So for every 1 liter, we have 1,000 milliliters. Now we can use this volume we were given. We have 6 milliliters right here over 1. We have that we were told we have that. So our milliliters are now going to cancel. So within that 6 milliliters, that's how many moles of silver we have. So let's just leave this as it is. So it's a 1-to-1 ratio from silver to zinc, or silver nitrate. So for every 1 silver nitrate, we have 1 zinc. And I know I should be using moles, but if I keep writing, my pen tends to start working weird, and I'm trying to avoid that at all costs. And so for every 1 mole of zinc, we have a certain mass of zinc that exists. So for zinc, that is 65. 65. See, I'm having to slow down. 65 grams. So we can use what we are given in order to move along. As long as we remember what molarity means, molality means, and percent mass, we can do these kind of calculations. And I'm going to do more of these in class when we're going over this, so please be sure to come to class. So 4 times 6 times 65 it's going to be 1,560 divided by 1,000. So we would only need 1.56 grams of zinc to fully react with those 6 milliliters of silver nitrate. So that's a fairly simplified version of a stoichiometric calculation you can use with concentration. Now, for dilutions, when you are doing stoichiometry, when you are doing reactions, you're going to need certain amounts of your solutes in your solutions when you go to do them. This is because we only want so much to react, and as things become more concentrated, they tend to become more dangerous to work with, so we have to be able to make dilutions. So with dilutions, there's two ways you can do this. You can either add a solvent, a pure solvent, or you can add a lower concentration solution to whatever you are trying to create. There are benefits and drawbacks for both of these, so if you're trying to make sure that you get just the right amount, it might be easier to do it with a lower concentration solution. If you're just trying to get it down quickly, then you want to add a solvent. So what we have is a simple equation to determine what our new molarity or our new volume would be. So I really usually care about the volume at the second point, or how much volume I need to begin with. So that's what we're going to start with, is how much volume we need of something to make something else, because that's the most common thing you're ever going to see. So let's say we have a 6 molar solution of NaOH, and we need to make a 0.5 molar solution, and I need enough for an entire class. So let's say I need 2 liters of 0.5 molar solution. So we start by plugging and chugging. So this is my 1s, and these are my 2s. So what you start with is always the 1, what you end with is the 2s. So I start with my molarity, so we have M1V1 is equal to M2V2. So my M1 is 6 molar. I know I have a solution, all I need that's 6 molar. I don't know how much volume of that I need in order to create my 0.5 molar solution and have 2 liters of it. So that's what we're trying to figure out. And it's very simple. We just solve for x. So 6, or 0.5 times 2, which is just 1, divided by 6 is the amount of material that I need. That's the volume I need. So I need 1/6 of a liter. So this would be in molarity, this would be in molarity, and that's in liter. My molarity cancels, and I'm left in liters. So I need 1/6 of a liter. Well, 1/6 is 0.166666. Oops, here we go. (0.1666) repeating. So if I want something I can actually use for this, because they don't make liters with this small of a measurement, I can convert this to milliliters, and that would be 166 0.6 repeating milliliters, which I can easily do. I would then take this amount and put it in something like a 2-liter graduated cylinder. Here's my little spout. So put it in a graduated cylinder, and then fill this up to 2 liters with pure solvent. So basically what I've done is I've taken the amount of moles I had from my molarity here at the beginning, and I am filling it to a certain amount to get this much. When I do that with a pure solvent, I use this equation. So you need to know this equation. Now, sometimes you have to be you want to be a little more precise with exactly how much you're adding. So in order to get those really precise measurements, sometimes you'll want to use a lower concentration solution in order to dilute it to make sure you don't kind of overshoot. In order to do that, you have to do a little more math work, but it's fairly simple. So let's say we have two solutions, a 3 molar and a 1 molar solution. So if we add 3 milliliters of the 1 molar solution to one beaker, and we add 8 milliliters, well, let's make it 7 to make it easy on ourselves, and we add 7 milliliters of the 1 molar solution, what will our new solution concentration be? So we can't use the M1V1 is equal to M2V2 because we have a concentration in whatever we're using to dilute with. So instead what we have is we have the final volume and we have an amount of moles that we can describe. So we have the mole from the first one plus the mole of the second all over the final volume. So our moles would be, for the first one, 3 molar, which is 3 moles per liter. So every time you see this capital M, you should automatically think moles per liter. So if that doesn't really work for you, then you would have a mole for every 1,000 milliliters. It's the exact same thing. So I have 3 mils, so I need to do 3 molar divided by 1,000 times 3 of those. So that would give me 0.009 plus that amount from the other one. So that would be 1 divided by 1,000 times 7, which is going to be 0.007. And then my final volume, well, that's 10 mils, but I need this in liters, so it's 10 milliliters, and there's 1,000 milliliters in 1 liter. So you're going to have 10 divided by 1,000, which is 0.01. So I'm going to just keep everything as decimal, so this is easy for me later. So I'm done with this. I just simplified this so that I wouldn't have to deal with it in just a second. So 0.09 plus 0.07 divided by 0.01. Let's find out what that is. 0.009 plus 0.00007 is 0.016. I then divide that by 0.01, and I get, at the end, 1.6, and this is still moles per liter, so it's still molarity. But what I want you to notice is that my 1.6 moles is between my first one and my second one. That's very important because it lets you know you did it right. Because no matter how much of this less concentrated solution I have, no matter how much of this 1 mole or 1 molar solution I add to this 3 molar, I can't make the molarity go up because I'm adding something less to something more, and vice versa. No matter how much of this 3 I add to this 1, I can't go below 1 because that's the lowest amount I have. So I have to be between these two numbers, even if it's 2.99999999999999996, it's still less than 3. So even if that was the case, it wouldn't matter because it would be still slightly less than the 3 molar. Now we would still round it up, so it's like it kind of didn't change, but when you get down to those small numbers, it really wouldn't matter. However, you would still know that I have diluted this ever so slightly. We'll be showing this more in class, so please make sure you are there for that. But that is everything that we need to talk about for molarity, solutions, and water. Starting next week, we'll be talking about acids and bases, so you really have to understand concentrations and how that works in order to work with those. I look forward to seeing y'all in class.